Ring opening substitutions of epoxides give us access to two substituted alcohols, alcohols with functional groups at the 2 position. And I love this slide because it contrasts strong nucleophiles versus acid catalyzed, where typically here we're using a weak nucleophile, and we can really see the complementarity of these two methods in terms of regioselectivity. We have, for example, a less substituted carbon and a more substituted carbon in this epoxide, and we can see that if we want to attack at the less substituted carbon, we can use a strong nucleophile like SR-, CN-, an alkoxide, even a Grignard reagent or lithium aluminum hydride, and we get the nucleophile adding to the less substituted position. If we want substitution at the more substituted position, we can use acid in conjunction with a weak nucleophile. So notice here we have the nucleophile linking to the more substituted position. And the alcohols versus alkoxides is a big distinction, where we can essentially get either regioisomer depending on whether we use basic conditions, strongly nucleophilic OR-, or acidic conditions with the weakly nucleophilic ROH. Epoxides are great for synthesizing alcohols with functionality 1 carbon away from the alcohol or hydroxyl-bearing carbon. And an example of that is this target right here with an OH group as the functionality that is adjacent to the alcohol. It's a diol, essentially, right? 2 alcohol groups. When we want to synthesize this from ethylbenzene, and this looks pretty interesting. We're starting with a pretty much unfunctionalized, nothing jumping out at us in terms of reactivity in this starting material. We're starting with this, and we want to go to something with functionality on these carbons that apparently are the ethyl group carbons in the starting material. So how do we even begin to tackle this problem? Well, I think here it helps to think retrosynthetically, and this is good advice for breaking down multi-step synthesis problems into manageable chunks. Start with the target and ask yourself, what functional groups are in this compound, and do I know how to make them somehow in just one step, going back to some other kind of organic molecule? And the answer is yes. I know how to make this via a anti-dihydroxylation reaction. That can take me back to this alkene, and I know I can make this diol via epoxide formation followed by, for example, acidic ring opening of the epoxide. Now, how do I make this alkene? Well, notice I also want to tack on some carbons onto the end of this ethyl group, and so I can think about doing that through an alkyne where the alkene is located, making this bond right here. But I got to get back to the alkyne first, and that can be done in the forward direction through a dissolving metal reduction, right? We know how to turn this alkyne into this transalkene through a dissolving metal reduction. And now I've set up a situation where this key bond that I need to make involves an sp hybridized carbon and an sp3 hybridized CH2 carbon. And we know how to make this bond via an SN2 substitution of an acetylide. So this is drawing on reactivity of alkynes that we've seen before. It's one of the only ways we know to make carbon-carbon bonds. And if we compare, again, the starting material to the final target, we'll see that we need to make a new carbon-carbon bond and tack on this 3-carbon fragment somehow onto the end of the ethylbenzene chain. And we can do that through an alkyne, which we've worked our way back to here. Now, what remains is for us to work this alkyne backwards to the ethylbenzene starting material, and we can do this by imagining that we can make the alkyne via halogenation followed by elimination, a dehydrohalogenation process where we use base to eliminate HX from the dihalide product of X2 addition, and then the alkene can be worked backwards to this alkyl halide, where again the carbon-carbon double bond comes from elimination of HBr in this alkyl halide, benzylic bromide, really. And noticing that that bromide is benzylic is key, because this means that we can work this backwards to ethylbenzene, imagining that we can do a radical halogenation of this carbon to install this good leaving group. And we've done it. We've worked all the way back to ethylbenzene. And if this looked like a lot, one thing I would encourage you to do when you're just starting out with synthesis problems is get your notes together and try to have a big list of all the reactions or flashcards of the reactions that you've seen previously that you can quickly kind of rifle through. Flashcards are really nice because you can sort of arrange them, right? You can use the flashcards to do retrosynthesis actively, putting cards in and out, moving cards around, switching steps around if needed, and these kind of long-winded retrosyntheses get a lot easier when you have that resource in hand. But in any event, these are all reactions we've seen throughout Organic Chemistry 1. And in the forward direction, we're just going to write the reagents required and double check that things will work as advertised. So we just mentioned that we can use benzylic bromination to install this bromine, and that's going to work great. We may want to use something like light along with the NBS as a reagent, just forgot to include it here. And then elimination, this is kind of a pick your favorite base situation since we only have one unique set of beta hydrogens here. And for example, NaOH and heat will do that elimination at the secondary benzyl halide quite easily. And then we're going to halogenate this. That's going to make the vicinal or 1,2 dibromide with Br2. And then we can eliminate that using excess sodium amide, NaNH2. Now, normally we would treat with water at this point to get the neutral alkyne, right? Take that terminal acetylide intermediate that's formed via this strong base and just protonate it. But here we actually don't even need to do that, right? Because we want to use the terminal acetylide as a nucleophile in the next step. So we can actually hit with this propyl bromide electrophile immediately to install the 3-carbon fragment through an SN2 reaction. We don't even need to isolate the alkyne, which is pretty cool. This takes us right to the internal or substituted alkyne, which we can hit with dissolving metal reduction conditions. That's sodium metal in liquid ammonia. That gives us the transalkene. That geometry is important if we're going to do anti-dihydroxylation, right? This geometry is what leads to this geometry in the final diol, and the anti-dihydroxylation conditions is where we see the epoxide coming into play. We could, for example, use MCPBA followed by opening in acid to generate the trans or anti-diol. So each step here is going to work as advertised. And in terms of the role of the epoxide here, was noticing that we had an OH group in the target with a functional group at the 2 position, or the carbon next door. This is often a dead giveaway for an epoxide involved in the synthesis, particularly when the functional group here looks like a natural nucleophile like water or an OR group through an alcohol or a cyano group or something along those lines.